Welcome to the public defense of PhD thesis entitled Silicon Germanium based multiple phase VCO operating for millimeter wave frequencies. My name is Deepa George and my supervisor is Professor Saurabh Sinha. This is the agenda of the presentation. I will start off with stating the hypothesis and follow it with the context of the research. The research questions investigated will then be discussed. This would be followed with the research methodology undertaken to validate the hypothesis. This involved analytical modeling of phase noise in a millimeter wave VCO configuration and also the design and layout of the prototype. The simulated and measured results of the prototype will be discussed. The last part of the presentation will discuss the design of the vector sum multiple phase generator and its simulation results. Finally, the conclusions derived from the research would be presented. The research hypothesis under investigation can be stated as if a linear time varying model could be used to analyze a millimeter wave VCO configuration, then an analytical expression for phase noise in terms of process and design parameters could be derived and optimized to improve the phase noise performance of the VCO. To elaborate this further, let me first provide a background to the research. The activity in developing millimeter wave systems started with the release of the unlicensed spectrum of 7 GHz at 60 GHz. The spectrum is available worldwide, though the band is slightly varied and 4 channel frequencies are allocated. The characteristic property at 60 GHz is that the atmospheric oxygen absorption peaks at this frequency, and hence this band is suitable for short range communication. Thus, the first application targeted at 60 GHz was the personal area networking space where wireless communication could be achieved inside a single room at data rates over 2 gigabits per second. Later in 2010, the WiGig Alliance was formed, which is now working towards achieving multi-gigabit wireless communication at 60 GHz. There are also other applications being developed in the millimeter wave range, namely vehicular radar at 77 GHz, passive imaging at 94 GHz, etc. In addition to obtaining high speed systems, the added advantage of moving to higher frequencies is the reduction in the size of the antennas, as wavelength is about 2.4 millimeters in silicon dioxide at 60 GHz. Thus, compact systems can be created, but the small size of the antennas necessitate highly directional beams for communication, which could be obtained using techniques such as phased arrays. This is also suitable as the behavior at V band is more line of sight and there is less diffraction compared to lower frequencies. A complete integrated phased array system consists of several antenna elements arranged in one or two dimensions, with each element having its own signal path. In a phased array transmitter, as in this figure on the left, the signals radiating from each element are delayed such that they add up coherently and thus transmit in the intended direction. In narrowband systems, the required time delay in the signals at each element of the phased array can be obtained by a phase shift. A phase shifter with a phase control range of 360 degree and a phase resolution of 22.5 degree is a typical requirement for phased array systems. The phase shift can be applied at the radio frequency, IF, or the local oscillator path. The advantage of LO path phase shifting is that the phase shifter loss does not directly deteriorate the receiver's sensitivity. The figure on the right shows the different phases of the local oscillator signal applied to the mixer as in a local LO phase shifting system. The experimental component associated with this research tests the feasibility and accuracy of a silicon germanium production technology based integrated phase shifted VCO for implementing a phased array system. To minimize the RMS phase error in the output of the integrated phase shifted VCO, a low phase noise VCO is required. In addition, the particular requirement of an oscillator in any communication system is the low phase noise of the oscillator. This is because the channel spacing is constrained by the phase noise. Hence, this research also targeted the improvement of phase noise performance of VCOs, particularly at 60 GHz, by studying the phenomenon of phase noise generation. I focused on analytically modeling the phase noise to optimize the design performance by identifying the high impact process or design parameters. Silicon germanium HBT is a modification over the standard silicon VGT in which the band gap energy of the base is lowered by introducing germanium atoms to its base. The lowered band gap in the base improves the emitter injection efficiency of the transistor. The high emitter injection efficiency enables one to increase the doping concentration in the base and thus lower the physical base resistance. The graded germanium profile in the base also results in a drift field which accelerates the electrons from the emitter to the collector, thus lowering the base transit time. Hence, silicon germanium HBTs have high unity gain frequency, as it could be noted from the equation that the base transit time is a major contributing factor for determining unity gain frequency. The low 1/f noise of silicon germanium also makes it the preferred choice over MOS technology for VCO design. This is because 1/f noise is upconverted and shows up as phase noise of the oscillator. The conversion mechanism will be discussed later in this presentation. The added advantage of integrating silicon germanium and CMOS technology into bi-CMOS processes is that it helps in the development of system-on-chip millimeter wave systems where analog, RF, and digital circuitry can reside on a single chip. In the IBM 8HP process, silicon germanium HBTs with FT of 200 GHz have been integrated into a 130 nanometer CMOS technology. The process also has model RF passive devices at 60 GHz, which are useful in millimeter wave design. The research questions investigated are: first, the feasibility of a vector sum interpolator that can provide multiple phase VCO signals for the local oscillator path shifting architecture of the phased arrays. As discussed earlier, the RMS phase error of such a system depends on the phase noise of the VCO as seen from this equation. Hence, another aspect investigated was the modeling of VCO phase noise in order to optimize the design performance with respect to the design and process parameters. This slide discusses the knowledge gap addressed in the research. The research work involved modeling the phase noise in a millimeter wave VCO configuration using the linear time varying theory for oscillators. This led to an analytical expression for phase noise in terms of impulse sensitivity function of the active device noise sources. The lumped element approach for millimeter wave design as followed in this research was tested out by prototyping. The schematics used the process design kit supplied by the foundry, and the measurement of the VCO indicated a figure of merit of 172 dBc per Hz. This figure of merit accounts for phase noise, center frequency, tuning range, and power dissipation in a single equation. Finally, the vector sum interpolator was also investigated for its suitability in millimeter wave phased arrays. This table gives the performance of state-of-the-art VCOs at millimeter wave frequencies. The figure of merit achieved with the fabricated prototype is typical in millimeter wave range. A higher figure of merit is reported in reference 5 but is achieved at higher power consumption, about twice as that of this work. The output power is not taken into account in the presented figure of merit, and that is the reason for the high figure of merit of reference 6. As can be noted, it provides very low output power. The reason for the low output power is that it is a push-push VCO in which the second harmonic is combined with the output to provide a higher frequency of oscillation. A push-push topology is advantageous in achieving a wide tuning range and low phase noise with low power consumption, as the tank operates at half the frequency. The disadvantage is that the power output at the second harmonic, which is a useful one, is very low. The vector sum method can generate a random phase signal by interpolating the in-phase and quadrature phase signals. The resultant magnitude and phase of the signal depends on the magnitudes of the quadrature phase signals as seen from this equation. The implementation of a phase shifter working on the vector sum principle has the functional blocks as shown in the block diagram. The VCO generates a signal which is passed through a 90-degree phase shifter to provide quadrature signals. The signals are then combined together by adjusting their gains using variable gain amplifiers. In this research, the 90-degree phase shifter was implemented using a launch coupler, and the variable gain amplifier was based on Gilbert mixer topology. The phase noise at an offset frequency, as seen from this equation, is the ratio of the signal power at the offset frequency to the power at the center frequency. The significance of phase noise has been discussed previously. For many years, it was LEESON'S model which interpreted oscillator as a linear and time invariant system that was used to provide an expression for phase noise. This expression was derived from the noise spectral density of the source as reflected at the tank. This indicated a 1 by f squared phase noise variation as seen from this equation. The LEESON'S model had to be adjusted to match the real oscillator spectrum, which had a 1 by f cube variation. It required empirical parameters f and also an expression to bring about the 1 by f cube frequency variation of the spectrum. The active device noise sources, which are energy restorers in an oscillator, had 1 by f noise spectrum, which indicated the reasons for the 1 by f cube variation, but it failed to explain the proper conversion mechanism of the 1 by f noise to the 1 by f cube variation of phase noise. But it was evident from the model that the phase noise decreased with increasing quality factor of the tank and increasing signal power. The concept of linearity and time invariance of oscillators in LEESON'S model were re-examined by MIEEE and Lee. They demonstrated that oscillators are time-varying systems, though linearity appeared to be a reasonable assumption as far as the noise-to-phase transfer function is concerned. To prove that oscillators are fundamentally time-varying systems, they considered an impulse at the input of a lossless LC tank oscillating with constant amplitude until the instance of the impulse. They analyzed the system's response to an impulse occurring at two different time instances. Each noise source may cause both amplitude and phase variations. It was observed that if the impulse coincides with the maximum of the voltage, the amplitude increases abruptly, but the phase superimposes with the pre-existing oscillation, and thus the timing of the zero crossings does not change. An impulse occurring at any other instance is seen to cause a change in both amplitude and zero crossings in the oscillations. Therefore, an oscillator is basically a linear time varying system with periodicity. The impulse response for the phase is a function of two arguments, the observation time t and the excitation time tau. Capital tau in the expression is the impulse sensitivity function and is a dimensionless frequency and amplitude independent function periodic over 2 pi that describes the amount of phase shift from applying a unit impulse at any point in time. Thus, the noise current is converted into excess phase. Since the noise to phase conversion is linear, excess phase could be obtained using the superposition integral of the impulse response of the system. This excess phase is then reflected as the output as phase noise. Though the equations are omitted on the slide, the conversion of circuit noise into phase noise is shown in the figure using the power spectral densities. The final equation of phase noise in the 1 by f squared region of the spectrum is given here. The key concept demonstrated in ISF theory or the impulse sensitivity function theory was that the impact of the noise sources that are activated during the operation of a circuit varies across the oscillation period. In other words, the same noise source generates a different level of noise depending on when it is active. Hence, if the operation of the oscillator could be controlled such that it delivers energy during the insensitive instances in an oscillation cycle, then the phase noise could be minimized. The collector voltage and current of an LC oscillator tank is shown in this figure. This shows how the current peaks at the peaks of the voltage value. So a cyclostationary noise source such as the collector current short noise source, which follows the collector current variation, should be modified to account for this time variation of the noise source in a cycle. These aspects of the linear time varying model were used in this research work, which attempted to model the phase noise in a millimetre-wave VCO configuration by analyzing the effect of the noise sources on the phase noise by evaluating the ISF of these noise sources. A cascode configuration of the common collector Colpitts oscillator is the most popular millimetre-wave VCO configuration. A basic core of the differential common collector Colpitts oscillator comprises two half circuits consisting of transistors, inductors, and capacitors. The tank is connected between the base and the emitter of the transistor, and the output should be tapped from the collector terminal by connecting buffers to it. N, which is a ratio of the capacitors, is a design parameter in the oscillator design process or experimental setup. The phase noise contribution of active device noise sources such as the collector current short noise and base resistance thermal noise is analyzed for a common collector configuration. The ISF of an individual noise source is calculated by injecting current impulse in parallel to the noise source, and its effect on the tank capacitance is evaluated by using small signal model circuit analysis. The approach followed to evaluate the ISF of any noise source is to relate it to the ISF of the tank resistance by evaluating the voltage change at the tank capacitance caused by the respective current impulses. The noise source of the tank resistance requires a charge to be injected at node A, and the collector current noise source requires charge injected at node B as seen from the figure. Noting the variations of the voltage across the tank capacitance due to these injected charges, the ISF of collector current short noise could be written as shown on this slide. This, along with the term alpha, which takes into account the cyclostationary nature of the noise source, gives the effective ISF of collector current short noise. This could then be used to derive the phase noise contribution from that noise source. Similarly, the base resistance thermal noise requires a charge impulse to be applied across the base resistance. The voltage variation that such an impulse would cause at the tank capacitance was evaluated, and the ISF was written in terms of the ISF of the tank resistance. The phase noise expression for this contribution was derived, and the two phase noise contributions were added together to obtain the final expression for phase noise. The final expression for phase noise was plotted to obtain the optimum value of the design parameter. This was performed by substituting the values for the other design parameters in the millimeter wave range. This table gives the design parameters for an oscillating frequency of 60 GHz. A tank quality factor of 6 is typical in the millimeter wave range, as this is dominated by the quality factor of the varactors. From the plot, it is seen that the optimum value of the design parameter was around 0.3. This is a circuit of the millimeter wave VCO that was prototyped. The tank inductors at the base of the transistors are presented with a negative real part and a capacitive reactance. This reactance is influenced by the varactor and helps in tuning the oscillation frequency. Q3 and Q4 form the cascode transistors used to buffer the tank from the load. As it is separated from the tank by Q1 and Q2, its impact on the phase noise is very minimal. The inductors at the collector of Q3 and Q4 form the output network designed to resonate at 60 GHz. Inductors placed in the emitter branch of the circuit implement the LC filtering technique commonly used to reduce the phase noise contribution of the current source. It also enables the use of a single current source instead of two. Other transistors and resistors constitute the bias network of the circuit, which supplies the oscillator current and also provides appropriate bias voltages at the required nodes. The circuit has three inductors in each of the half circuit: the tank inductance at the base, the inductors in the output network at the collector, and the inductors at the emitter used for phase noise minimization. The smallest realizable inductance in the process was chosen for the tank to maximize the varactor capacitance, which in turn maximizes the varactor quality factor and thus the tank quality factor. The inductors in the collector and emitter are realized using RF line components available in the process. The tank inductance was realized using microstrip lines available in the process. The microstrip lines were connected such that a virtual short is achieved at their ends. After selecting the minimum realizable inductance value, the value of the required tank capacitance is determined by the desired oscillating frequency. Apart from the passives in the tank, the transistor parasitics also influence the oscillating frequency. Thus, it required fine-tuning of the capacitances C1 and C2 for a specific oscillating frequency of say 60 GHz. Numerical simulations using SPECTRERF were performed to test out the accuracy of the analytical model. The design parameter n was varied by changing capacitance values, and the phase noise values were plotted for each capacitance set. As seen from the plot, the phase noise simulations indicated that capacitor's ratio of about 0.3 provides best phase noise performance. Thus, the SPECTRERF simulations also verify what was found through the linear time varying theory. The varactors available in the process have been simulated to compare their performances and to observe whether they cover the desired tuning range. The capacitance and the quality factor were obtained from the S parameter plots according to the following equations. It was observed that junction varactors have higher quality factor and MOS varactors have higher voltage tuning sensitivity. Thus, the junction varactors were used in the implementation of the VCO as they have a better quality factor and tuning range than the MOS varactors in the millimeter wave range. Varactor quality factor was also found to improve with reduced width and an increased number of base stripes because of a reduction in the base resistance. The figure on the left shows the entire chip where the VCO was fabricated along with two other projects. The 60 GHz VCO implementations are highlighted in the figure. The figure on the right shows the 60 GHz VCO. The VCO was laid out symmetrically and the differential outputs were connected to the ground signal ground pads which was spaced 50 micrometers apart. The IBM 8HP process used for the design is a 5-level metal technology. The interconnect lines and the inter-level connections were designed to adhere to the standard electromigration rules that sets a maximum value of the DC current and also local heating enhanced electromigration that sets a maximum value of RMS current. The measurements were performed at the wafer level as interconnects like bond wires which are used to attach the die to the package influences the MIMIC performance. The figure on the bottom shows the MIMIC on the probe station with the ground signal ground probes placed on the pads for measurement. As the measurements were performed with the help of a probe station, the pad's layout and its pitch should adhere to the specifications of the probe used. A block diagram of the entire measurement setup is shown here. The PCB was placed on the wafer probing station. The ground signal ground pads on either side of the MIMIC were contacted with the ground signal ground probes attached to the probe station. One port was terminated with 50 ohms and the other was connected to a spectrum analyzer through a V-band mixer in order to extend the operation of the spectrum analyzer in the 50 to 75 GHz range. The probe station, spectrum analyzer and the Pico probe used for measurements are shown here. The VCO drew a supply current of about 35 mA from a 4-volt supply. The sender frequency of 52.8 GHz and the corresponding phase noise value at 1 MHz offset of minus 98.9 dBc per Hz was measured. The tuning voltage was varied from 2.5 volt to 6.5 volt and a tuning range of 50 to 57 GHz was obtained. The simulated and measured tuning ranges are displayed and a 10% variation was observed. It was reported in a paper published recently given in reference 14 that when a silicon germanium BiCMOS technology is used for fabricating LC-VCO, the capacitance variations lead to a 10% variation in the frequency range. So that explained the frequency variations that was observed in the measurement. To further investigate the vector sum interpolator, large couplers were used for quadrature signal generation. They are popular in the millimeter wave region because of their low insertion loss. The large coupler basically consists of 4 interconnected metal lines and there is a 90-degree phase difference between the through and coupled ports. The process design kit for the 8HP process provides the behavior-based model for the large coupler that accounts for the losses, coupling and silicon substrate effects. The plot at the top gives the gain and the plot at the bottom shows the phase difference between the signals from the through and coupled ports. It can be observed that the phase difference varies linearly in the bandwidth of interest from 57 to 64 GHz, and this is because the coupler is designed to be of length lambda by 4 at the center frequency of 60 GHz. The variable gain amplifier for the vector-interpolator was implemented using a Gilbert mixer topology. In the figure, resistors R1 to R4 were included to increase the linearity of the amplifiers. The gain control voltages are generated using a pre-distortion circuit, which is an inverse tan cell, so as to improve the linearity further. The plots give the gain characteristics of the variable gain amplifier and the simulation results of the interpolator. The gain varies almost linearly with the control voltages applied to the pre-distortion circuit. A variation from 0 dB to minus 30 dB was achieved with a gain control voltage variation from minus 0.8 volt to 0 volt. The simulation results of the entire vector interpolator system could be seen from this plot. The vector interpolation provided yellow signals with phases ranging from 0 degree to 360 degree in steps of approximately 22.5 degrees. The maximum phase error over the entire range was about 8 degrees. The interpolator consumed about 24 milliamperes from a 2.5 volt source. Thus, to conclude the presentation, the research work conducted through this doctorate study performed the phase noise modeling of the VCO using the linear time varying theory. The optimum value of the design parameter was found to be 0.3, which was then verified using numerical simulations performed by SPECTRERF. The prototype VCO reported a figure of merit of 172 dPc per Hz. The results of the tuning range of the measured VCO indicated a 10% design margin for the tuning range to be accounted for the capacitance variations in the process node. Finally, the simulation results of the vector sum interpolated indicated its suitability for millimeter-wave phased array systems, but as the correctness of any IC design has to be verified by its measurement results, it would have been fully characterized if it had also been prototyped in the IBM 130 nanometer process. These are the journal publications resulting from the research work. Both are peer-reviewed journals listed by the Thomson Reuters Web of Knowledge or ISI. The PhD thesis associated to this work provides a full bibliography, but those references used for this particular presentation have been listed here. Finally, I would like to thank the National Research Foundation in South Africa and the National Authority for Scientific Research in Romania for funding, travel and associated cost enabling for measurements related to this work. And thank you for listening to the presentation.